Hi everyone, welcome to my presentation on improving image classification with location context. The original work was done by members of the Stanford Computer Science Department. If we view the four images presented, we can conclude that all four images can reasonably be snow. However, image A was taken in Bonneville, Salt Flats, Utah, C was taken in Death Valley, and image D was taken in Palo Alto. None of these locations have ever seen snow. Only image B, taken in New Hampshire, truly contains snow. Motivated by this, members of the Computer Science Department of Stanford have taken an approach to utilize embedded GPS coordinates within images to provide reasonable context for images using geographic data, surveys, as well as other internet-provided information. I would encourage anyone interested to view the entire research paper, as this summary will only provide a small snapshot of the research. The research presented relies heavily on the CNN architecture, which is the basis for the most state-of-the-art image classification and recognition results. I'll not go into much detail about this model, but each feature described in this presentation is built into the CNN model. GPS encoding. Many images uploaded on the internet today contain embedded GPS coordinates due to widespread availability of cell phones and other GPS-enabled cameras. The first step in location classification is leveraging the coordinates. However, the coordinates are too fine of a classifier to use effectively. For the purposes of research, the continental United States was cut into a rectangular grid with a latitude to longitude ratio of 1/2, and an indicator vector for each image was constructed to indicate which grid cell the location fell in. The result of this was a feature vector with dimensions equal to the total number of cells in the grid. Each grid contains 25 by 25 square cells. Geographic map features. There exist many different types of geographic map and datasets. Using indicators from these maps, we may be able to determine how likely an object may appear. For instance, using a topographic map, the elevation would tell us how likely it is to see snow, or an image from a high precipitation region would have a higher likelihood of having an umbrella. This research used 10 different maps representing average vegetation, congressional districts, ecoregions, elevations, hazardous waste, land cover, precipitation, solar resource, total energy, and wind resource. Since each map uses different colors to represent the value of a feature at a particular location, for each image I, a normalized pix color in a 17 by 17 patch around the GPS coordinates is taken for each map type and concatenated to form an 8670 dimensional feature. ACS feature. Another online resource to leverage are geographic surveys. Using GPS coordinates, we can obtain the corresponding zip code, and with it, get access to surveys collected by agencies and organizations like the U.S. government. The American Community Survey, ACS, is an ongoing survey that provides yearly data on age, sex, race, family and relationships, income and benefits, health insurance, education, veteran status, disabilities, work status, and living conditions, organized by zip codes and pooled over a 5-year period. Each statistic is treated as an additional feature and results in a 21,038 dimensional feature. Age and income are indicators that could be used to tell us how likely a toy or an expensive car would appear in the image. Hashtag context feature. By using images on Instagram, correlations can be made to distributions of hashtags and geographical locations. Hashtags that commonly occur near an image can help indicate types of real-world context of that image. The first step is to identify a set of hashtags we are interested in. We then obtain a set of images correlating to a specific hashtag of our set. Next, we define a radii set R, and for each radius of set R, we pool over a circle radius around the GPS location and count the number of images tagged with the hashtag. Here we have a visualization of how the hashtag context feature was built. We'll go over the determination of the radii shortly. but it's worth noting that the hashtags in the inner radiuses are weighted more than hashtags in the outer radii. Hashtag, hashtag context normalization. With the datasets obtained, the feature must now be built. There are two normalizations for the hashtag set counts in each radius r of radii r. We normalize each count by the sum of counts for all hashtags, which gives us an idea of the relative frequency of a particular hashtag in relation to other hashtags that appear over an area. For the second, we normalize each hashtag count by the total number of images obtained from Instagram with, with a particular hashtag. This will provide an estimate on how often a single hashtag appears over a region in relation to over the entire United States. The visual context feature is similar to the hashtag feature, except we take advantage of the visual signal around our GPS coordinates. Each image is run on a CNN model to generate probabilities of 594 common types of concepts, such as clothes, girl, coffee, etc. Once again, a normalization is taken. For each radius r in our radii set r, we sum the probabilities of all images that fall into the radius r for each concept, resulting in a set of 594 by r probabilities. We perform the same two normalizations we did previously on these results to obtain a 2 by 594 by r dimensional feature. The same set of radii r in GPS quantization is used as the hashtag feature context. Optimal pool radius. As mentioned with the hashtag and visual context, we use a radii set r, and not any set would be informative. A difference of a few kilometers may be an important indicator for some of the more rare hashtags or concepts. To obtain the optimal pooling radius, a CNN model is used to construct the layers automatically, also called a radius learning layer. First, a single hashtag or concept is considered, and a function is fit over the histogram that returns the value of the histogram feature for hashtag and radius at a location given by the GPS coordinates. This is done for every hashtag concept and both types of normalization schemes to obtain a set of 2 times h plus 594 histogram functions for each image. To evaluate all the research and features built, the Yahoo Flickr Creative Commons 100 million YFCC 100M was used. This contains 100 million images from Flickr. 49 images contain geotags. From the 49 million, manual verification selection methods were used to identify important tags and disregard images that did not actually contain the tag noted. Researchers also had to be selective on location-sensitive classes. Data needed to be limited to a manageable number of classes, and images for notation needed to contain a non-normal geospatial distribution to confirm location context methods. By using the Kullback-Leibler divergence, a comparison was made between the normal geospatial distribution of all images and the geospatial distribution of a particular tag. The resulting dataset contained 88,896 manually verified images with the highest KL divergence. Here we can see the below tags with the highest KL divergence, location-specific places such as beaches, Disneyland, mountain, or snow. Now we're getting on to the results of this research. The two graphs show the best and worst results of implementing the geographical feature recognition functions. Highly localized tags such as Disneyland, casinos, and Alcatraz see a large increase in average performance. On the other hand, some of the worst performing recognition was on car brands. This perhaps suggests that car classes are not very location specific. Here results comparing baseline image model to the best model, both correct and incorrect. The images on the left-hand side were identified incorrectly on the baseline. With the new models, they are now identified correctly. However, on the right-hand side, we see images that were identified correctly with the baseline, but are now identified incorrectly. In conclusion, this research captured 5 features regarding location context to better identify images. There was an increase in image recognition, but even the top performing images only attained a 7% increase in recognition. This underlines the difficulties faced by computers in object recognition. Researchers noted that in the future, taking advantage of time and date stamps on images or the social relationship between the users could provide an increase in performance. Thank you.